Problem 21.6. So consider the problem of minimizing x2 subject to this constraint. There are three questions. First question, find all the points that satisfy the KKT condition. Second is for each x star, we find in question 1, find the corresponding t x star, n x star, and t2 x star. The third one is to find the points in one that satisfies the second order sufficient condition. Actually, this is very typical steps that we're going to do when we see a constraint inequality constraint problem. So let's see how to do this step by step. So the first step is to form the Lagrangian function. So Lagrange function is just the f of x, which is this, plus mu times gx. So the f, as you can see, fx is just x2, where x is just has two variables. There are two variables involved. The g, there is only one inequality constraint, so I will just have the g here, one g here. The g is, I move everything to the one side such that it's less than or equal to 0. So apparently in this case, I should have negative x1 minus 1 squared minus x2 plus 3. Okay, and this should be less than or equal to 0. So the Lagrange condition is f of x plus mu times gx. So this is g, this is the mu. The KKT condition is the to compute the partial derivative or to compute the gradient of L with respect to x. Essentially, just compute the partial derivatives of L with respect to each of those variables, x1 and x2. So for partial derivative with respect to x1, we get this and set to 0. A partial derivative with respect to x2, we get this and set to 0 as well. And this one is essentially just the original inequality constraint, gx less than or equal to 0. This is the requirement for the of the non-negativity requirement for mu, for the KKT multiplier. The last one is the slack completeness condition. And then to solve this, try to solve this again. Try to solve this, and we'll get the only solution like that. So that is the only point that satisfies the condition. And actually, we also need to check if this x star is a regular point or not. So in this case, you can see that mu is equal to 1. The constraint is actually active because when you plug in 1 and 3 here, you see that is equal to 0. So that constraint is also active, so we just need to take the gradient of g, that is, or the Jacobian of g, and that matrix, as we'll do here. The g is this, right? The gradient of g is this. So at the point 1, 3, you will see that this is equal to the 0, negative 1 vector. And this is a full rank 1 by 2 matrix. So that's why the point x star must be a regular point, and that's also justifies that x star is a KKT point. And now to get those three sets, the first set t x star is supposed to be the null space of the Jacobian of the active constraint, vector function formed by the active constraint functions. There is only one constraint function that is active, and that's the g. So the gradient of g, as we said, this is just the 0, negative 1 matrix. So the null space, I should say this is null, not this n. The null space of this will be, as you can see, the second component has to be 0. If you want to multiply any two-dimensional vector, take the inner product of any two-dimensional vector with this vector, you get 0. Then the second component, the first component doesn't matter, it always gives you 0. The product with 0 is always giving you 0. The second component, the inner product, second component, the product should be also 0. So that's why this is a null space. So all the vectors that are of this form are in the null space of this. So you can see that the inner product of these two will give you 0. So that's the tx star. The nx star, maybe just here. The nx star is just an orthogonal complement of tx star. So just collect all the vectors that are perpendicular to every vector in here, and that is just this. So it's the vectors of forms S a 0s. The first component has to be equal to 0. Second component must be equal to s. Must be can be any vector. Can be any scalar s. And finally, for the t tilde, we need to look at the constraint G, and we know that the corresponding mu is non-zero, right? Mu is equal to 1. So in this case, the t tilde is just the t, which is the null space of the gradient of G, and that is this space. So I just copied it here. Okay, that's t tilde. So that's the second question. The last question is to actually show use the second order to check if this point x star satisfies the second order sufficient condition. So to that end, we need to form this Hessian or weighted sum of the Hessians. So the f is this. The f is this. The gradient of f is this. And the Hessian of f is this. And then the gradient of g. We already know g. What is g? And the gradient of g is this. The Hessian of g is this. And then you take this weighted sum, and then you get that. Okay. So now you can see. Well, now we can see that for any vector. For any vector y in this t tilde, the y has to be in this form, right? It should be a t0, some kind of for any t, for some t. Okay, so for any of such vector, this y transpose times this weighted sum, which is this one, and we'll calculate this, just plug in y and also the matrix inside. We get this. And that's strictly less than 0 for any t not equal to 0. So that means we can find many y that are in this t tilde, but this product gives us some negative number. So that means the x star does not satisfy the second order sufficient condition. Okay, if it satisfies, that means you need to show that this guy is greater than 0 for any non-zero t. But apparently this is not the case. This is exactly the opposite, actually. Not exactly the opposite, so it doesn't satisfy that. Okay, so that's the answer.